who somehow still have managed to not memorize those trig derivatives, I promise you they are not going away. We're going to need them next quarter too. So just figured it was good to start off with a little practice. The derivative of cosine of x is? Sweet. Derivative of tangent of x? Derivative of positive sine of x is positive cosine of x. How about the derivative of secant? Okay, I got fewer vocal strong responses to that one. So make sure you include that in your list of things that you're memorizing. And now just for fun, if I take the derivative of natural log of something, I end up with 1 over that something times the derivative of the inside. So chain rule says I've got to multiply by, perfect. Here, I know that I've got product rule because I've got x squared times e to the x. So when I take that derivative, the derivative of the x squared is going to give me 2x. I'll leave the e to the x alone. I'm adding that to leaving the x squared alone. And the derivative of e to the x is e to the x. Sweet, we walk away. Okay. I posted into Canvas some practice problems that I'm going to use to kind of frame our discussion today. But at this point, we're talking about differential equations. We started off with some vocabulary, thinking about whether things were autonomous, pure time, or non-autonomous. And now we've got some new vocabulary, and the new vocabulary, I think, is more helpful because the new vocabulary is what allows us to decide how we're going to approach solving the differential equation. So our two kind of new vocabulary pieces are separable and first order linear. By the way, the first order linear stuff, it's not really in our textbook. So I have posted just some additional notes on that in Canvas to kind of walk through where the formula comes from. I know that Challenor did that in class also, but kind of just wanted to share that with folks. So let's talk differential equations. I mentioned that we have kind of these two new vocabulary words that are going to help us decide what we're doing with the differential equation. And those two words are separable and, okay, first order linear is not a word, it's a phrase, but I've got separable and first order linear. Well, what it means to be separable is that if I can get the part with the derivative by itself, and the other side of my equal sign looks like some function with only x's times some function with only y's, then I can separate things out to their respective sides. So if I look at this, it doesn't immediately jump out as being separable, but I can do a little bit of work to force it to look separable. That first thing I'm going to do is to get the y prime part by itself. So I'm going to add 3x squared y to both sides. Now, in order for this to look separable, there's got to be something that I can factor out so that I'm making the right-hand side look like multiplication or division. And in this case, that x squared is what I can pull out. And I've got something that looks like only stuff with x's times something that looks like only stuff with y's. If I take that y prime piece and I actually rewrite that as dy dx, this is what lets me shift my x's around to one side and my y's around to the other side. One of the things about these separable differential equations, We never get to choose which side each letter goes on. What I mean by that is we don't have a way to take the integral of something times 1 over dx. That's not a thing. But I can take the integral of something times a dx. So when I'm looking at this, I don't get a choice. I have to multiply by dx on both sides so that it's not in my denominator anymore. And once I've done that, that's telling me, okay, all of my x's need to stay on the right-hand side and all of my y's need to end up on the left-hand side. And we never get a choice of which side those letters go on. So I've got 1 over 1 plus 3y dy is equal to x squared dx. And once I've got all my x's on one side, all my y's on the other, then I'm ready to find both antiderivatives. And I'm going to give you all a minute to find those antiderivatives on your paper. Keep rolling here. So I'm going to do the easier side first. And I'm calling this the easier side. X is raised to powers, add 1 to that exponent, divide by the new exponent. Make sure to throw a constant somewhere. On the left-hand side, we can do this with a u substitution or not. I'm going to go ahead and write out the u substitution really quick by letting u equal 1 plus 3y. I know that my du is going to be 3 dy. Since I don't have a 3 on the top, I'm going to rewrite that to say 1/3 du is equal to dy. Now I'm kind of just going to draw a line here for a second. So now when I make that u substitution, I can throw that 1/3 out in front and I have 1 over u du. Which means once I find that antiderivative, I'm looking at 1/3 natural log absolute value of u. I'm going to pause for a second and say that in particular, when we're talking about differential equations, and especially when we have initial conditions, it's really important to keep that absolute value in there. Because sometimes our initial conditions are going to mean that what's inside of our log would have actually been negative. So we've got to make sure to keep that absolute value. Now I can swap that back out to say 1/3 natural log absolute value of 1 plus 3y. And that whole thing was equal to x cubed over 3 plus a constant. Some of the problems on your homework, we literally could not solve and rearrange for y if we wanted to. This one, however, we can. So let's go ahead and do the algebra to get that y by itself. And I'm going to pause for a second to see if there are questions up to this point. Yeah.
And so the reason why you can have a plus c on the other side is because you can subtract it from the.
Right. So each of these could potentially give us plus a constant, but they're not necessarily the same constant. So if I subtract it over, we're kind of just going to group those constants together again. Okay, time for some algebra. So I've got 1/3 ln 1 plus 3y in my absolute value, x cubed over 3 plus a constant. Now, I'm going to do a very mathematician-y thing. And as I move through this, I'm going to keep collecting my constants together. So my first move here, I'm going to multiply everything by 3 to get rid of the fractions. That's going to leave me with natural log absolute value of 1 plus 3y is equal to x cubed plus 3 times a constant. The mathematician-y thing to do is to say 3 times a constant is still just a constant. It's some other constant, but it's still a constant. What happens if you're looking at problems like this in the textbook is it might call that a C with a subscript of 1, and then group this whole thing together and call it a new constant, C2. You do not have to do this. I'm just doing it to illustrate a point. Okay, this next piece is what allows us to handle the absolute value well. How do I get rid of a natural log? Oh, that was a really bad way to say that. How could I rewrite this without a natural log? Yeah, so if I do that, I'm going to have absolute value of 1 plus 3y equals e to the x cubed plus c2. This next move is a super mathematician-y thing to do. And I would say that the natural log is the reason that we do it so often. If I had, I know I'm like filling up random little bits of space here. If I had 5 to the 2 plus 4, yes, that is 5 to the 6th. But what's another way that I could have written that? I do not want you to do 5 to the 6th out. Just looking for other ways that I could rewrite this piece. That's just kind of using our exponent rules. So right here, I have e to the something plus something, which means that I can rewrite that to be e to the x cubed times e to the c2. I don't know what this constant is, but I do know that e raised to a constant is still a constant. So I can do the mathematician-y thing and just call that whole piece C. Since we haven't actually figured out what that constant is yet, it means I don't know whether it's a positive or a negative number, which is great because I can drop the absolute value. Because that constant is now going to suck up the fact that it's either positive or negative. This is way more algebra in the weeds than you might need to be, but these kinds of algebra tricks are super common if you're looking through solutions or if you're trying to see if your answer matches something in the back of the book. So my last 2 steps, subtract a 1, divide by 3. So I'm going to say y is equal to ce to the x cubed minus a 1 over a 3. And if you wanted, you could take that c over 3 and just call that another constant, or I could just leave it right there. I'm actually going to go the extra step and make that ce to the x cubed minus 1/3. And just so that I've been consistent about my labels, I'll call this whole thing C3 so that my final answer is the one that just has a C in it. By the way, we had technically solved the differential equation way back here at this step. And if that's as far as you got, you would get most of the points on the problem, right? However, we're usually looking for a solution that looks like y equals or x equals or w equals or t equals, right? Pick a letter equals, not something where they're all mixed up together. linear. So let's talk about those words. So the first order part means that I only have a first derivative. I don't have a second derivative or a third derivative or a 12th derivative. I just have a first derivative piece. That's my first order. What linear means is whatever variable we took the derivative of, in this case, y, anywhere else the y shows up in the equation has to be raised to the first power. That's all it means to be linear. So I know that my variable of interest here is y. That's my dependent variable. And so anywhere else it shows up, it has to have an exponent of 1. That's what makes it linear. Now, the other way to think about this is that it's first order linear if there's a way to write it that looks like my derivative plus some function that can only have x's in it, or t's if t is your independent variable, times a y plus, sorry, not a plus, how about an equal sign, equals some function that again only has x's in it. So this happens to be first order linear because it follows this pattern. I can write this as y prime plus negative 3x squared times y is equal to x squared. So my p is negative 3x squared and my q is x squared. Do you all want to see where the process for first order linear like derives from, or do we want to just use it? I'm good either way. Just use it? Okay, so the whole idea with first order linear is some old dead white guy mathematician looked at this thing and was like, it kind of looks like a product rule. I'm just going to force it to look like a product rule. And the way we force it is by finding what's called an integrating factor. So the first thing that I have to do is to find the integrating factor. Our book it's not in our textbook. Most textbooks use the Greek letter mu, but I noticed Challoner is using a V. So I'm going to use a V so that notation wise we're consistent here. But if you're like looking up something on YouTube, you're probably going to see the Greek letter mu for the integrating factor. We're going to use V. And the way that we find V is always the same for a first order linear. We're going to take e to the integral of whatever our p function was. So I'm going to have e to the integral of negative 3x squared dx. What do we get when we integrate negative 3x squared? Perfect. So this is going to look like e to the negative x cubed. Now, the reason that I don't have to put the plus c is that if I have a plus c up here in the top, I know that we can rewrite that using our exponent rules as a constant times e to the negative x squared. And that constant is going to fall out of the problem later. So I don't have to worry about it now. So whenever we do this kind of intermediate step of finding the integrating factor, I don't have to put a plus c up here. What we do next with our integrating factor is to multiply our entire differential equation by that integrating factor. So I'm going to have e to the negative x cubed y prime plus e to the negative x cubed times negative 3x squared y equals e to the negative x cubed times x squared. So by the way, if I had that constant right now, that constant would be here and here and here. And since it's everywhere on both sides of the equation, I could just divide by that constant and it would be gone. So we're saving ourselves the trouble. We're not bothering to write the constant here because it was just going to go away in that next step. Okay, now onward with the fun. Now at this point, what we have on the left-hand side is supposed to look like a product rule. And it should always be exactly the same product rule. It should always look like we took the derivative of y times the integrating factor. So we can pause and check, and if we have done everything correctly, that's what should happen. So with my product rule, I had a take the derivative of y and I'll leave the y alone. And I had a leave the integrating factor alone. And if I take the derivative of e to the negative x cubed, I get e to the negative x cubed times, chain rule says, I've got to multiply by negative 3x squared. So this whole part came from the derivative of my integrating factor. So it worked. Our product rule piece worked. Go math. Since my product rule piece worked, over here on the right-hand side, I still have that e to the negative x cubed times x squared. And now is the part where we sort of solve the differential equation. Well, solving the differential equation means I've got to take an antiderivative. This thing is already a derivative, so when I take the antiderivative, I just get the thing back. But I have to actually take the antiderivative over here. So on this u substitution, I'm going to go ahead and let u be equal to negative x cubed, because then my du is negative 3x squared dx, which I almost have. I just don't have that negative 3. I've got the x squared in the dx part. So I'm going to make that say negative 1/3 du is equal to x squared dx, which lets me swap out this integral. Oh, I'm going to go ahead and put my negative 1/3 out in front. You can put it inside. It's okay. I just think it's a little cleaner to put my constant out in front. Sorry, scoot that up. And then I'll have e to the u du. When I integrate that, I'll get negative 1/3 e to the u plus a constant. And if I swap that back out, that means I've got negative 1/3 e to the negative x cubed plus a constant. Now that whole thing, if we were following the left-hand side down, I'm going to have y times e to the negative x cubed. If I do that last algebra step to get the y by itself, I'm going to divide everything by e to the negative x cubed. Super common place to make a mistake. If I divide everything by e to the next x, I can't talk. If I divide everything by e to the negative x cubed right now, it's going to cancel out right here, but it will not cancel out from the plus c. Super common mistake to forget about that plus c or to think about adding it on to the end it's important that we put it in right when we take this integral. So I'm running out of space, but I'm gonna actually write it out because I think it's important. Just because I've seen so many mistakes made. So these don't really cancel out until I think about this as two separate fractions. So if I think about this first part of the fraction, the e to the negative x cubed does cancel out and I'm left with -1/3. And on this piece, you could leave that as c divided by e to the negative x cubed, or I could write that as c times e to the positive x cubed. Okay. Is that what we got before? Moment of truth. It is what we got before. If the problem is first order linear and also separable, not very many problems are, but if it is, then you, generally speaking, have your choice, do whichever thing feels easier. So my first check is to say, is it separable? Well, if it's separable, then there must be a way for me to rewrite all this stuff on the right-hand side as stuff with y's times stuff with x's. And it looks like if I just kind of regroup this as y over y plus 1 and x sine x, that sure looks separable to me. It is not linear. And the reason that it's not linear is if I look at this part, whatever kind of algebra you want to do, you've got y's in the denominator, which means we're going to end up with some kind of y to the -1 power. So it's not linear. We have to solve this as separable. We would also know that because it was on homework 13. But in terms of the quizzes and midterms, you will have to look at the problem and identify how we're going to approach it. So it is separable. I don't get a choice of where my x's go because once I multiply by dx to make that cancel out, I know my x's are going on the right. There is a question in the chat that I do think is important to address. And it kind of just comes down to how fractions work. So multiplication and division are commutative, fancy words for really getting at the point that if I have 3 times 2/5, that's equivalent to 3 times 2 divided by 5, and it's also equivalent to 3/5 times 2. As long as all the pieces that are being multiplied end up in the top, and all the pieces that were being divided end up in the bottom, I can rearrange and regroup things. So that y plus 1, everything in my numerator was multiplication. There's no addition in my numerator. So we're not like distributing a y plus 1 to build multiple fractions that are being added or subtracted. I'm just regrouping the pieces for the multiplication. Don't know if that helped, but kind of how fractions work. Yeah.
Did you restate why it's how you know it's separable?
So anytime I can write it as stuff with y's, multiplied by stuff with x's, It's separable. The book writes this as something like separable differential equations can be written as f of y times g of x. So I've regrouped it. So I've got stuff with y's times stuff with x's. I know it's separable. And now I can separate and get things on each side. So when I go to move things around, just because that got a little bit messy up there, I'm going to give myself some space. So I have y over y plus 1. And then x sine of x dx. So my x's are already where they go. I just have to get the y's to the other side. Lots of different ways to show this. What I'm going to do is I'm going to multiply both sides by y plus 1 and divide both sides by y. That way, my y over y is a 1, and my y plus 1 over y plus 1 is a 1. Now, on the left-hand side, unlike where we started, now I do have addition in my numerator. So thinking about that with fractions, now I really do want to break that up as two pieces and call that y over y plus 1 over y. I'm going to take care of the left-hand side because it's going to be our more straightforward piece to find the antiderivative of. Y over y is 1. I really meant to just thinking about a y in my head. I just wrote a y on the top. That's really a 1 over y dy. So that's all ready for me to find the antiderivative. Antiderivative of 1 with respect to y is a y. And the antiderivative of 1 over y is going to give me natural log absolute value of y. Now I get to do the right-hand side. Right-hand side is going to be a little more fun. I've got multiplication. So I've got two things being multiplied together. There's not going to be algebra to get me out of this because I've got a trig function. So there's only two options for that multiplication. It's either a u sub or it's integration by parts. What's the derivative of sine? I don't have a cosine anywhere in there, so that u sub is not going to help me. A u sub where you let u equal x is never helpful. It just trades your letters. It doesn't actually do anything for us. So this side's going to have to be integration by parts. So I know that I'm going to end up with u times ultraviolet voodoo. So u times v and v du. So I'm going to have x times negative cosine of x minus the integral of negative cosine of x dx. I always pause here when I'm doing integration by parts to multiply through any constants or minus signs before I do the next step. So that means I'm going to put that minus sign out in front. Minus a minus will make that a plus the integral of cosine of x dx. And now I'm going to go ahead and integrate that. And the function whose derivative is cosine is positive sine of x plus a constant. Now, one of the questions that I've been asked a lot about this particular problem in office hours is how do you solve for y? The answer is you don't. This equation has a fancy word that we can use to describe it. This is transcendental. That means there's no algebra we can use to isolate the x or the y. So this is as far as we can get. Now, how would we know that? The issue, if we think about the y's, is really that I've got something inside of a natural log and something else floating around out here. And that other thing that's floating around out here, there are no log rules that would allow me to put those together. So if I, for example, subtracted y from both sides and then did e to the y, then I would have just moved an e to the y to the right-hand side. I wouldn't have actually kept the y's together in any way. And if I just did e to the y on both sides right now, this wouldn't simplify because I have a y plus something. Same kind of thing would happen with my, if I tried to isolate the x's because of that x times cosine of x. There's no way to algebraically solve that. So that's the best we can do. Except this one had an initial condition, so we ought to be able to get to the c. And the initial condition on this one was written as y of 0 is equal to 1. And just as a reminder, that notation means x is 0, y is 1. So if I plug those in to solve for my constant, I'd end up with 1 plus natural log of 1 is equal to 0 times cosine of 0 plus sine of 0 plus a constant. And most of that goes away. Natural log of 1 is 0. 0 times something is 0. Sine of 0 is 0. And we just get that the constant is equal to 1. So my final answer on this one would look like y plus natural log of y is equal to negative x cosine x plus sine of x plus 1. And excellent question in the chat. If you want to do the practice quiz and want feedback from me on it, absolutely, I will give you feedback on the practice quiz. So a few people have already turned it in. I'll give you feedback on it. If anyone else wants to, regardless of whether you're actually enrolled or not, you're always welcome to turn in the practice quizzes for feedback. Okay, so my question doesn't ask you to solve this thing, doesn't ask you for much. It just says, if we know that p of 0 is equal to 1, what's the limit as t approaches infinity of p of t? So here's the thing. If p of 0 is equal to 1, that means I'm starting right here. What's the value of the derivative? Right. If my derivative is 0, is my function changing? So if my derivative is 0 and my function is not changing, this limit is 1 because I'm stuck at 1. 1 is in equilibrium. If I had asked you any point other than 1, this would have been a more complicated question. But really, this was just meant as a, do we understand the connection between this graph and that being in equilibrium? By the way, if I were going to draw the phase plane for this, it's kind of a weird phase plane. So I know that if I started anywhere between 0 and 1, these derivatives are all positive. So my p-values would be increasing. But anywhere from 1 to infinity, these values are also all positive. So my function is increasing. So technically 1 is not locally stable. It's like one-sided stable, but from the other side, it's unstable. So sometimes we call that semi-stable, but it is not locally stable. Okay, so this is number 5 from my practice sheet. And if what I asked us to do was to solve the differential equation, we really only have 2 techniques so far in this class. Either it's separable or it's first order linear. So I actually think that first order linear is easier to check for. And the reason I say that is to check for first order linear, I just have to figure out what did we take the derivative of? What are the powers of that letter? This is not linear because I have an x squared term. If it's not linear, then it's probably separable. If we've been asked to solve it. And if it's separable, I am trying to have my derivative equal to something that I can factor to get the x's by themselves and the y's by themselves. What do we think? Do we want to practice actually finishing this off? Yeah? Okay. Together or on your own? How about if we take a couple more steps together? Okay. So I know that if I'm going to separate it, I don't get a choice of which side my x's go on, which is kind of unfortunate for this problem because it means that I'm dividing the whole thing by y squared plus 6y. And it is important that we are dividing the whole thing by y squared plus 6y. The right-hand side is going to be straightforward. The left-hand side, all of our techniques of integration are still carrying through with us. So when I look at this, I'm going to walk up to that integral and say, oh, it's really just algebra stuff. Can I make it look like y's raised to powers? And I can't because of the addition down there in the denominator. So instead I go, oh, hey, it's a fraction. I wonder if the bottom factors. Since the denominator does factor, I'm thinking about partial fractions. Because I'm looking at something 1 over y times y plus 6 that I'm going to want to rewrite as a number over y plus a number over y plus 6. I will let you refresh your memory and do the partial fractions part. So on the partial fractions, if I multiply through, I'll have a times y plus 6 plus b y. And it looks like our nice numbers to plug in are 0 and -6. For both of those, there's nothing to plug in on the left-hand side. I just have a 1. So if I plug in 0, I've got a times 6 plus 0. And if I plug in -6, I've got 0 minus 6 B. So I get that A is positive 1/6 and B is negative 1/6. And I'll go ahead and send this back to the place. I'm going to squeeze this in. So if I squeeze this in, I know that my left-hand side now should look like the integral, and I'm going to put my numbers out in front. So I would have 1/6 of 1 over y minus 1/6 of 1 over y plus 6. Both of those are going to lead to natural logs. So I'm looking at 1/6 natural log absolute value of y minus 1/6 natural log absolute value of y plus 6. Now, somewhere way back up here, I also had this right-hand side of the equation. So I'm going to pop it in. And the integral of x squared is going to look like x squared over 2 plus a constant. I mentioned on that problem from homework 13 that there was no way to solve to make it say y equals. That is not the case for this one. I actually can solve to make this say y equals. Do we want to do that algebra or just call it good there? Do the algebra? Okay. I definitely do not have space for that in this, so I'm going to flip the page. I'm just going to rewrite it.
Oh.
Yeah. I got to rewrite this whole thing on the next line. So I've got 1/6 natural log absolute value of y minus 1/6 natural log absolute value of y plus 6 is equal to 1/2 x squared plus a constant. You have choices. Come on, focus, focus. Okay, we have choices here, but I'm going to multiply by 6 so that I don't have fractions anymore. I'm going to write that as natural log absolute value of y minus natural log absolute value of y plus 6 is equal to 3x squared plus a constant. And this is where I'm going to go ahead and label that C1. I multiplied everything by 6. So I'm going to call that C2. It's not the same constant, but it is a constant. Subtraction between logs, that I can combine together. So that subtraction between logs, I can turn into y plus 6 over y. And that I can do e to the stuff on both sides to get rid of my natural log. Yeah. I don't know. I got it backwards. How about a y over y plus 6? Better? Okay. Now I can do e to the stuff on both sides. When I do e to the stuff on both sides, got y over y plus 6 equals e to the 3x squared plus c2. And that's where I'm going to rewrite that as c3 e to the 3x squared. And once I do that, that constant is going to take care of that absolute value. So I don't need the absolute value anymore. And I can say y over y plus 6 is equal to c e to the 3x squared. Now, it may look like we still can't solve for y. We can, we just have more algebra in our future. I'm gonna stick this whole thing in a box for myself for a second. So if I stick that whole thing in a box, then this looks like y over y plus 6 equals my box. I can multiply both sides by y plus 6. And I can distribute my box so that I have the box times y plus the box times 6. And if my goal is to get the y's together, I'm now going to subtract this over so that I've got y minus my box times y equals the box times 6. I can factor the y out. And finally, divide that whole thing over. Now that I'm ready to divide the whole thing over, I'm going to actually write out what was in the box. And in the box, I had CE to the 3x squared. That's times 6 over 1 minus CE to the 3x squared.